Okay guys, welcome to birthday coding session 1. I got this fucking thing working. Pretty cool. So this is the dual. But it's the dual driving a single motor in parallel, so it can drive in theory maybe twice the amps continuous. So if you have just one big motor and not two smaller motors, then you can just drive it with one dual. And it will show up in the interface as a single motor. It appears as just a single VESC, but yeah. So it's a completely separate firmware that you upload, because it's would be dangerous to be running dual firmware in a config setting. It could be done as a config, but I think it would be more dangerous. Like, this needs to be very intentional because you're shorting the phases together. In theory, the overcurrent thresholding should catch if you did this incorrectly and not damage the unit, but I haven't tested it yet, and I'm not really keen to test it because it's kind of scary, because you essentially would get shoot through of the FET. So all these FETs are being driven in parallel each phase, and then what that does is you essentially get twice the FETs per phase, so you get half the total resistance in the system. I mean, it makes perfect sense, right? You can push two motors each at 80 amps continuously for like indefinite, or you can push one motor at 160 amps. It's logical. But yeah, as you can see, it's all wired up like this. The motor is spinning. I don't think I have it calibrated particularly well right now, but you know, whatever. Okay, so what are we doing now? Now we are going to do some thermal testing just to see if this passes some sanity checks, right? So let's turn off this, let's turn on the heartbeat, let's turn on real-time data, and let's go and do an FOC open loop test. So what we're going to do is 50 amps at 1000 RPMs, that's what this means, and we're going to watch the FETs heat up. So let's go over here to real-time data. Right now we're starting at 30.2 degrees, that's my room temperature. You can see I have no heat sink on the dual right now, so it should heat up relatively quickly at 50 amps because there's almost no thermal mass. So without further ado, let's get going. And let's go into real-time data, and you can see the FETs are already climbing. We're at 32 degrees. And then we will just cut power around, I don't know, let's do 50 degrees maybe. So yeah, spinning up 50 amps, we're at 6.5% duty cycle or so. This is a good way to tell that we're driving the same amount of current. Is we should be close to the same duty cycle on the single side FETs. It'll be slightly higher because we have the intrinsic resistance of the FETs in a loop, but not that much higher, because you could think about it this way. The FET resistance is probably a total of about 4 milliohm, and the motor resistance is probably about 10 milliohm. So you can expect to be about maybe 15 to 20% higher on a single set of FETs, but nothing more than that. So we might be at like 7% or 8% duty cycle when we switch over to single side FETs. Okay, but we're heating. We're at 43 degrees C right now. Maybe we won't go too hot because it'll take a really long time to cool down, and I'd like to just do this video in a continuous shot because I'm not editing anything on my fucking birthday. Okay, yeah, 45 will stop. And we might just do a differential temperature if this thing's taking forever to cool down. So we heat it up 15 degrees, so whichever temperature we start from next time, we'll stop 15 degrees above that. Realistically, like, it's slightly better to be hotter because you cool off faster, so you have more temperature going to the ambient. But without a heat sink or anything, it's really not that much of a difference. And as long as we cool down to maybe 35 C, you're really not going to see that much of an advantage. These things are just barely warm here. I'm going to set the camera down and unplug one half of the phases now. The cool thing is that all this stuff still runs just like normal when you just plug in only half the phases, because all of the current measurements are just summed, and you actually end up with twice the resolution on your current shunt amplifiers into the ADC, which is kind of a little added benefit of this topology. And you also could, theoretically, if you wanted to make a really beefy one, you could drive twice the FETs in parallel because you have twice the motor drivers, right? So you have twice the FET drive current. So it's kind of an interesting concept and something you can only do with this kind of dual architecture. Okay. And another cool thing is, like, imagine if you had a build where, like, you actually had the ability to drive that much power. You had some huge motors, but maybe at the time you only had money for one motor driver. You could buy one drive both the motors off a single motor, and then later on, when you save up money, you could buy a second one and then drive both of them at twice the continuous amps. It's really kind of interesting and modular, this setup. So so we're connected now. We're down to 35C, and we're at just half the phases connected. So let's run this from the top. We're going to start at probably 34 by the time I get around to clicking all this stuff. And then we'll go over here to real-time data, and you're going to see the temperature heats up just way faster. And the reason that is that, again, there's no heat sink, and we're generating twice the power. And it's not just twice the power, it's twice the power in half of the area, because only one half of the FETs are being recruited right now to drive this motor. And so you can see, I think we started at 34, so we should stop at 50. We probably already overshot that by a lot because we're at 60. But you can see it heats up just way, way faster. What duty cycle were we at there? I didn't see. Yeah, let's just run it again. Oh, I didn't hit that heartbeat. Oops. I just want to know what duty that was. But yeah, you can see, as I said, we're at about 7% duty. So we are pushing the same amps through the FETs. But yeah, the heat generated, as you can see, it heats way quicker. So yeah, this is a super cool option. I think it's a very interesting way that you can configure the motor driver. So I'm really excited about the possibilities here, and I have a lot of different ideas from this. I mean, I drove back from San Francisco last night and I had this. Well, we already thought about doing this 100 times before, but I kind of like realized the correct way to do it and how easy it would be now, thanks to Ben Vetter. He helped me to kind of rehash the dual in the current latest firmware, and when we did that, the refactoring produced it into an architecture that is much more modular, and so it's much easier to take this and just add in a quick, simple change. Like, to give you an idea, I started coding at 7 a.m. today, and it's now 9:45, and I'm done. Like, I'm very confident that this is the finished product. So yeah, it was super easy, super fast, and I'm really excited about the possibilities of this. Thanks for watching.